now we are done with the passive high pass filter first order, because we have only one stage. And here the same story. So here in the low pass filter, we are talking about the falling. So we were talking about the low pass and then the falling slowly, and then the output becomes zero. Because this is high pass, so the opposite. So it's just rising slowly, and then output is going to the maximum at the high frequencies. This is the high frequency. So how fast this slope is rising, the linear exponentiation or the linear raising. So that is what we are going to talk now. So here we have this high pass filter. It's linearly increasing towards the maximum of the output value at the high frequency. So it's not a sharp raising. So you can see the ideal filter, it is going sharply up, vertical line. But here in the practical filter, it is going linearly. But what we want, so at high frequencies, we really want this output as the maximum value. At low frequencies, we do not want any output value. This is the low frequency region. This is the high frequency region of the input signal. So in the low frequency, but still we are getting some output if the curve is going slowly up. So we want to sharply make it up. So how can we do that? Then we have to move to the higher order high pass filter. Same logic as the low pass filter. So how can we design the higher order filter? Same. So we have to cascade more number of stages. The simple high pass filter, you have to cascade one after another, then you will get the higher order filter. For example, this is the second order high pass filter. If I put one more stage here, then it will be a third order high pass filter, and fourth order, fifth order, and so on. So the performance of this two-stage filter is equal to single stage filter, but the slope of the filter is obtained at minus 40 dB per decade. So here for the single order filter, it's increasing minus 20 dB per decade. For the second order filter, you have to just multiply this by 2. So then it will increase minus 40 dB per decade. So remember, this is something you have to remember. And then if you design third order filter, then this minus 20, that is the base value, multiplied by 3. Then it will increase minus 60 dB per decade. So this curve will become more and more sharp. So you will get more sharp raising. So in the low pass filter, we were talking about more sharp falling. Here we are talking about sharp raising. So the same principle as LPF, cutoff frequencies varies. For two-stage filter, the cutoff frequency will depends on the values of two capacitors and two resistors. That's correct. C1, C2, R1, R2. Okay, so here is the formula for cutoff frequency. 1 divided by 2 pi square root of R1 C1 R2 C2. So if you make the value of R1 is equal to R2 and C1 is equal to C2, then it will become R square and C square. Then the square root will be gone. Then finally you will still get the same formula, 1 divided by 2 pi RC as the cutoff frequency for this higher order filter. So if we cascade more poles, then output will reach the maximum value faster. So this roll off will be very fast. Roll up will be very fast, and it will reach the maximum output value quite fast when you go to the higher order filters. And the phase shift of the output signal is leading the input signal with an angle of plus 45 degree. The output voltage will depends upon the time constant. This is the time constant value, 2 pi RC, and the input frequency applied to the circuit. So the same formula for this higher order filter, a higher order high pass filter. phase shift formula is turn inverse 2 pi r 2 pi f RC omega RC, and the output voltage is, this is the formula. So when you talk about is it easy to implement this higher order high pass filter, the same principle or the same story again. So there are challenges to cascade these R and C stages together because we have the loading effect problem. So same challenges as the LPF. So active high pass filter is the best choice. So what does it mean? What does it mean? This is the passive high pass filter, right? But when we go to the higher order, then we have a problem. So we are moving to the active high pass filter or active higher order high pass filter. So active means we are going to introduce the operational amplifier between them. Then it will isolate the loading effect, and it will also amplify the input signal at the output. And the output of the operational amplifier as given as the input of the second stage. Output is always less than input in the passive filters, that we know that because it's using only R and C elements in the circuit design. So whatever input you give, if you give 1 volt, you will get at the output maybe 0.9 volt. It's not a matter, it's a low pass filter or high pass filter, because it's using only the passive elements. But if you introduce active elements like op amp inside, then 1 volt if you apply, then you will get 2 volt or more based on the gain. Okay, so when you cascade more stages, output will be much smaller than input voltage. That is true for the passive. Here we have the passive higher order filters. So the output will become, for example, I apply 1 volt, I get the 0.9 volt at this stage, and then I am applying 0.9 here, and then I am getting maybe 0.8 or 0.7 here, and then the third order, then I get 0.7. So the output becomes more and more less when it becomes higher order passive filter. There is also loading effect. So active filter is the better choice to overcome these drawbacks. So active filters are using operational amplifier or transistors together with R and C. So now we know what is passive high pass filter. It can be a single pole, single pole or one pole, or it can be a two pole, or it can be a three pole. So here, for example, this is a two poles. This is the pole 1 and this is the pole 2. It means it's a stage 1, stage 2. So I can cascade more and more. So when I cascade more and more in the passive, then output is getting more and more reduced. So if I apply 1 volt, I cannot get the output like a 1 volt, at least 1 volt at the output. I will get more and more down. So that's not what I want. So I do not want my filter to eat the magnitude of my input signal frequency, input signal magnitude. So I want the high frequency signal only at the output, but at the same time, I want same amplitude or I want a higher amplitude. I do not want the amplitude to get reduced. So then we are going to the active, instead of passive, we are going to active high pass filter. So here, this can be a one pole or first order filter, or it can be a second order, or it can be a third order. So it's up to the designer and application. Where do you want to use this filter? If you want a very sharp rising, then of course you have to go to the higher order. But you don't mind, it doesn't need to be very sharp. It's okay, linear region, maybe second order filter is enough.